Hello, everyone. I'm Bokai from the University of Illinois at Chicago. And I'm glad to be here to present our work on the collective fraud detection capturing the intertransaction dependency. And this is a joint work with my internship mentor at Electronic Arts, Mia and Sim, as well as my PhD advisor, Professor Philip Yu. So fraud detection from a supervised learning perspective is essentially to do a prediction or classification problem. Conventionally, in currently many fraud detection pipelines, we just train a workflow, train a machine learning classifiers based on all the given attributes and features to classify whether this transactions is fraud or not. And in our case, in particular in the electronic arts, we have the game product types. We have FIFA, Star Wars, as well as we have payment types, the PayPal and the Visa and the MasterCard, all these different attributes informations. So in this case, we can just concatenate all this information together and feed them into a classification algorithms to get a model to automatically identify these frauds. However, all these features, from a graph mining perspective, they are just different types of entities. So in this case, we can, instead of treat them independently in order to create them together, we can create links between different types of entities. So in this case, we can to form heterogeneous information networks from this toy example. Essentially, the heterogeneous information network is a type of networks that contains multiple types of nodes or multiple types of links. And in our data sets, we collect our data in EA and we construct this kind of network schema as shown in the right figure. So in this case, we have transaction as one type of the most important entities. That's our target we want to predict. As well as we can connect different other types of entities, including IP address, as well as the billing IDs and countries. All this information can be correlated together to form a large information networks. And in these data sets, it spans 83 days in last year. And in this schema, it contains 12 node types and 15 link types. And in these 83 days, there are 400,000 nodes in this data set, as well as 1.5 million links in this network. So one interesting question we can extract from this network schema we just constructed is that how do we define the similarity between different transactions? So the idea we use here is the so-called metapath. So metapath is a sequence of multiple different link types. For example, in this case, we can connect two different transactions based on metapaths using different semantics. For example, in the first one, in the first metapath shown in this table, we can see that these two transactions are connected if they are associated with the same billing IDs, and these two billing IDs are registered in the same IP address. So in this sense, we can connect these transactions together. And similarly, we can define these similarity-based transactions in other semantics. And these are the 10 different examples of this metapath we can extract from this schema in our data set. So how do we compute this metapath? So mathematically, usually we just compute the metapath by using a chain of matrix multiplication. But this will introduce a lot of redundancy because if we, for example, in this case, if we want to see whether these two transactions come from the same source or from the same IP address, essentially we just we just multiply the adjacency matrix of the transaction to IP address and the transpose of this matrix together to get the similarity between the two transactions. So in this case, you can see there's several distance blocks in these right figures. So that's not desirable in our algorithms. So luckily, we are not interested in the similar transaction themselves. What we are interested in is to compute dense features from out of these similar ones. So we want to aggregate all this label information of these similar transactions to see what is the fraud ratio of these similar ones. For example, if the current transaction are coming from a particular IP address, and we have some histories about this IP address. We want to see what is the fraud ratio in that IP address so that we can put this information in our classifier models. So in this case, we can avoid directly computing this metapath itself. So we can firstly aggregate this label information in a pre-computed downsized metapath, and then we can pairwisely we can combine this downsized metapath together in the training and test process. So as shown in the right figure, the algorithms we propose in this work is essentially a iterative classification. It's so-called collective fraud detections. So at the first step, we will initialize this test label of these transactions using the existing features in our systems. And then we will extract the features from the networks, and we see what is the fraud ratio in the similar transactions based on the network schema. And then we will update the predicted labels for those test transactions. And based on these predicted labels, we will update the features, since the features essentially are the fraud ratios in the both training set and test sets. So we will iteratively do the training and test. And in our experiments, we use sliding window techniques, and based on this, we can sample 7 different subsets from our collected data. And essentially, in each subset dataset, we use the previous 10 weeks as training, and we use the following 1 week as test. So in this case, we just compare our algorithms with the baseline methods. The baseline is just using some given existing the features in our system, and the heat fraud is our proposed one. We just add those new metapath-based features as well as the collective prediction techniques in this existing system. And basically, we can apply this idea with different types of underlying machine learning algorithms, including random forest and SVM and logistic regression and factorization machine. For example, here we can have a look at the leftmost columns, the 2 columns in each subfigures. This compares our algorithms with the baseline using the random forest as the base classifier. So we can see that by using our proposed techniques, we can get nearly 80% improvement in recall metric, and we can get about 6.6% improvement in terms of F-score. Similarly, we can see in the other precision and accuracy matrix. And as we said, since our proposed algorithm essentially is an iterative training and test, so in practice, we definitely want to make it more efficient, since we do not want to get such benefit by training and test the algorithms by hundreds or thousands of more times. That is impractical in industry applications. So in the following experiments, we want to see our algorithms can indeed converge in a very few iterations. So in this figure, we show an example using the random forest as the base classifiers. So we can see that since we are using the baseline, the existing features to initialize our algorithms, so we just put the performance of the baseline in the iteration 0, since the x-axis is the number of iterations, and the y-axis is the percent of improvement we can get in terms of 4 different metrics. So in here we can see, usually we can get a very significant improvement in the very first or 2 iterations, and the performance will become stable in the following later iterations. So that's good, we can converge very fast. And in this case, we can, as we said, we can get a very large benefit, significant benefit in terms of recall and the F-score. But notice that in some data sets, we have to sacrifice some precision. But in practice, especially in our scenarios, we would claim that it's a worthwhile trial in some scenarios, since this increased false positives will go through this manual review process. So if we just use this predict score as an assistant for manual review, so we would say we can sacrifice this no more than 1% precision to get this 8% improvement in recall. So I think that's a good trade-off we can try in practice. So here we come to the conclusion of this work. And so in this one, we propose how to do this fraud detection in the heterogeneous networks, and the existing many approaches basically focus on the homogeneous or the bipartite graphs. And the second one is that we propose to add these MetaMask features that those features can essentially can be more effectively to distinguish the suspicious transactions from the normal ones. And the idea of collective predictions has the potential to detect the suspicious transactions in the case that in a semi-supervised manner. So since in some cases, those very suspicious transactions may not be detected by those traditional or not graph-based algorithms, because in some cases, probably some transactions looks normal in many dimensions, but in some similar ones, in some similar other related transactions, they must have revealed some suspicious trace in other fraud attacks. So in our graph-based approaches, we can detect such common trace between those similar transactions, even those transactions are in the test subset. So in this case, we can more efficiently and effectively to identify those suspicious transactions. And yeah, that's the end of my presentation. Any questions?